Hello, everyone, and welcome to Algebra 2. This is section 9.7 on trigonometric identities. So a trigonometric identity is a trigonometric equation that is true for all values of the variable for which both sides of the equation are defined. That's a little bit of a mouthful, but we'll go through that in a minute. We are going to use trig identities to evaluate trigonometric functions, to simplify trigonometric expressions, and to verify other trigonometric identities. But before we start doing those things, on this page is a list of all the identities that you need to know. So the one that might be familiar to you is this first one, the reciprocal identities. We've talked about how sine is the flip of cosecant. And that one's not listed here, but if you just list it one way, then it holds true both ways. But I'll write it for you also. Cosine is the flip of secant, and tangent is the flip of cotangent. So that's the one that you might already be familiar with. We've talked briefly about this next one, how tangent is sine over cosine. And just in case you forgot why, remember that tangent is opposite over adjacent, where sine is opposite over hypotenuse, and then cosine is adjacent over hypotenuse. So if I multiply this fraction on the top and on the bottom by hypotenuse, I can do that because I'm doing it to the numerator and the denominator. This cancels, and you see I get opposite over adjacent. Or you could think of it instead as your traditional keep, which would be to keep this one the same, change, and then flip hypotenuse over adjacent. Either way, you're getting opposite over adjacent. And you could go through that same exercise for cotangent, but cotangent is going to be cosine over sine. The next set are super important. We're probably going to use this more than any of them. They're called the Pythagorean identities. You may remember the Pythagorean formula says that in a right triangle, where A and B are the legs of the triangle and C is the hypotenuse, A squared plus B squared is equal to C squared. So if you think about sine as being opposite over hypotenuse, but since it's squared, opposite squared over hypotenuse squared, and cosine as being adjacent squared over hypotenuse squared is equal to 1, then if I clear my fraction by multiplying both sides by hypotenuse squared, then on this side, when I distribute hypotenuse squared here, this is going to cancel. And when I multiply it here, it's going to cancel. And I'm going to get opposite squared plus adjacent squared is equal to hypotenuse squared, which is a squared plus b squared is equal to c squared. If this is theta, opposite squared plus adjacent squared is hypotenuse squared. And again, I'm not going to show you that exercise for all three of them, but I wanted you to understand why this identity is true. And then we'll use it for a variety of things. The cofunction identities we talked about briefly during graphing. Remember that sine's graph looks like this, and cosine's graph starts here and then goes like that. So how much are they off by? 90 degrees. So if you just shifted sine or cosine 90 degrees, then you would get the other one. So that's what these two represent, and the same is true for tangent. The negative angle identities don't come up quite as often, but I really want you to understand why they're true. Let's take sine of pi 6. Sine of pi 6 is 1/2. If I asked you to find sine of negative pi 6, you would say, well, sine of negative pi 6 is in quadrant 4, and sine is negative in quadrant 4, and then you would use pi 6 as your reference angle, and sine of pi 6 is 1/2. So you see what it is? Sine of pi 6 is 1/2, and sine of negative pi 6 is negative 1/2. So people think that you're just taking out the negative. You are not taking out the negative. This is a fundamental fact based on its quadrant. And just to prove that point, notice it doesn't work for cosine because you're not taking out the negative. Cosine of pi 6 is the square root of 3 over 2. Cosine of negative pi 6 is still the square root of 3 over 2 because pi 6, when it's in quadrant 4, when it's negative pi 6, has a reference angle of pi 6, so it has the same value, the same ratio, but in quadrant 4, cosine is positive. So it actually doesn't matter if you're at pi 6 or negative pi 6. Cosine is adjacent, which is positive, over hypotenuse, which is always positive. It has nothing to do with this opposite side, and that's the opposite side is the one that goes from positive to negative. So since cosine just has the adjacent side, it stays positive in both quadrants. So hopefully you can do that same exercise for tangent and see why this is true again for tangent, because tangent does involve the opposite over the adjacent. So of course it does matter if you're in quadrant 4. So tangent is negative in this quadrant. Okay, so let's get to work. Our first example is actually just a little bit of review from 9.1. I'm not sure why they throw it in again, but it's an important thing to know how to do, so let's do it again. Your book actually does it a little bit different. They use the identities, but I see no reason not to continue to do this the same way that we did in quadrant 1. Take your information and make a triangle. So sine is opposite over hypotenuse. Using the Pythagorean theorem, you can get this side is going to be 3. A squared plus b squared is equal to c squared. It does tell me the quadrant. You always need the quadrant in order to determine the sign, S-I-G-N, positive or negative. So in quadrant 2, only sine and therefore cosecant are positive. Tangent and cotangent, or tangent and cosine are going to be negative. So let's see, we have sine. I know, I'm just going to rewrite it. It seems a little silly, but then it's really easy to do. And cosecant, which is 5 over 4. And then cosine is going to be adjacent over hypotenuse, but I'm in quadrant 2, so it's negative, which means secant is going to be negative 5 over 3. Tangent is opposite over adjacent, but since I'm in quadrant 2, it's negative. And cotangent is going to be negative 3 over 4. So if you were to look at this example in the book, they would be using these identities to figure them out, but there's really no reason to do that. There's no reason not to just continue to use the triangle. I will say, though, that some people prefer to draw the triangle in the correct quadrant. So somebody might sit there and draw it here in quadrant 2, as it's supposed to be. This is 4, this is 5. And then since I'm in quadrant 2, I've gone into the negative x. So this would be negative 3. And then instead of using forecast, the triangle is appropriately labeled to put the positives and negatives where they belong. Like I said, I do it the blue way. I'd rather just always make a triangle, not think about where the quadrant, exactly how to draw the triangle in the correct quadrant, and then use forecast. But there's options. You guys are smart. You should do it the way that works for you. Okay. You might want to stop and write down on your appendix all the trigonometric identities, because now we're working on the back side of that paper and you're going to need to be able to look back and forth. But pretty much what we're going to do is make replacements that allow us to simplify. So pretty much if you ever see this, you want to simplify that. That's no good. So tangent of pi halves minus theta can be replaced with cotangent. That's on your identity sheet. And then I'm going to rewrite sine. Every step has to match, has to be equivalent. And then I'm going to replace cotangent, going up to your cotangent and tangent identities, as cosine over sine. And this is times by juxtaposition in math means multiplication, but sometimes it's nice to put the dot there. And when you're doing a fraction times a whole, some people prefer to make the whole into a fraction because it helps them see numerator times numerator, denominator times denominator. Although in this case, I'm multiplying by sine and dividing by sine, which are inverse operations, so they undo each other, and I'm left with just cosine. And that's how you can simplify tangent of theta minus, or pi halves minus theta times sine theta. At any point, you could stop and try these on your own. So on this next one, I'm going to leave sine. We usually leave sine, and we usually change things that are not sine, cosine, or tangent. So I see a cotangent. I'm going to change that to cosine over sine. And a secant, I'm going to use my reciprocal identities and change that to 1 over cosine. So one strategy, actually I'll do a strategy here first, is just to use the identities. Look things up when you don't know them. So this is just straight up an identity. But then another actual strategy is to change everything to sines and cosines. A lot of times when they're in similar trig functions, then you can cancel things, which of course I can here. My cosines cancel and my sines cancel. If it helps you, you can put that over 1, but this is definitely a numerator. And then when everything cancels, what do you have? You just have 1. And that's the answer. That's what that simplifies to. So whenever you see a square, you should be thinking about the Pythagorean identities, but especially if you see a square plus 1, which I don't see. Another strategy I'd like to show you today is factoring. And since that's the main strategy for this problem, I'm going to show you that first, but then I'll show you a second way to do it. So secant of theta, I'm going to factor out. Leaves me with tangent squared theta plus 1. And then now I'm going to use my identity. Like I said, if you ever see a tangent or anything squared and a 1, go over to your Pythagorean identities. And sure enough, this is secant squared. And then that gives me secant cubed theta. So a little bit harder way, but we're going to need some harder things in the future. So I just want to get your mind thinking about it, is I want you to recognize that while we were able to get 1 plus tangent squared theta, sometimes you can't always get that. You can think about this identity in 3 different ways. This is the main identity, but let's say I subtract 1 from both sides. This is the exact same identity. And some people find it useful to know more than one form of it. Let's see how that would have played out for this one. If somebody sees a square and they say, oh, I see a square, I'm going to go use the Pythagorean identity. When they have both of these written on their paper, then they would have changed this to secant, so tangent squared theta, I'm going to replace with secant squared theta minus 1. And then don't forget, there's still a plus secant theta. And now instead of factoring, you're just multiplying. So that gives me secant cubed theta. I'm distributing the secant minus secant of theta. I'm bringing this down, don't forget it, and secant of theta. And that simplifies to, because the 2 secants cancel, just secant cubed theta. Notice they both got the same answer. So if the first thing that comes to your mind is, I see a square, I'm going to use the Pythagorean identity, go for it. If the first thing that comes to your mind is, oh, they both have a secant, I can factor that out, that's also a great way. You're definitely going to have choices in this section. All right. So for letter D, now you have to choose which way you're going to do it. So I am going to do it by factoring. This gives me 1 minus sine squared theta. But unlike letter C, where this was so easy because tangent squared theta plus 1 was on your list, you see a 1, you see a squared, but the list for this one is sine squared theta plus cosine squared theta is equal to 1, which isn't what you have. So you might want to write down after your main one what some of the variations are. So let's say I subtract sine squared theta from both sides. Another variation of this is cosine squared theta is equal to 1 minus sine squared theta. This is the exact same identity. Just because somebody chose to write it this way on your sheet doesn't mean that they couldn't have written this one. This one's really good. Or let's say that instead of subtracting sine squared, let's say somebody had chosen to do minus cosine squared theta on both sides. What would that have given them? That would have given them sine squared theta is equal to 1 minus cosine squared theta. All three of these identities are awesome. If you're thinking, is there a third way to arrange this one up here? There is. So another way to do this one would be 1 is equal to secant squared theta minus tangent squared theta, just in case you're trying to make a very complete appendix. These are the three versions. I mean, there's more versions, but these are the three main versions for this one. And these are the three main versions for this one. And if you have that version, then this is a very easy problem. Now you can keep the cosine, and you can replace this 1 minus sine squared with cosine squared. And my final answer is cosine cubed theta. That's how you simplify that. All right, so let's say that you didn't think of that. We've talked about this with the last one. You don't think of factoring. You just see the sine squared and say, oh, that's on my list. I'm going to write this. So you replace the sine squared with 1 minus cosine squared. That's great. It's a great way to do it also. I distribute the cosine, and I get cosine of theta plus cosine cubed theta. And these two cancel, and I'm left with cosine cubed theta. Same answer either way. All right, now this one is really tricky for people because you want to change everything to sines and cosines, but if you do it right from here, some people get a little confused by the sine over cosine, and then this is 1 over sine, but it's a complex fraction because that's just the numerator. And then the denominator is 1 over cosine. We'll continue to do it this way, but I'm going to give you some other options. So then I can cancel the sines, and this becomes 1 over cosine over 1 over cosine. So I was going to keep, change, flip, or flip and multiply, but I almost don't need to. I can see that they cancel out, and I'm going to get 1. So another way to do this, if you're really bad at these complex fractions, is to change them to just be multiplied. So cosecant of x times 1 over secant of x. Think about why that works, because this is tangent times cosecant is my numerator, so I can put it over 1, times 1 over secant. I'm kind of just pulling that out and giving it a 1 to hold the place to make sure I keep it in the denominator. But if I were to multiply numerator times numerator and denominator times denominator, I'd be right back where I was. Some people prefer this because then they can change tangent to sine over cosine, cosecant to 1 over sine, and they can take 1 over secant and say, oh, that's cosine, and they just change it to cosine. Of course, you get the same answer. The sines cancel, the cosines cancel, and you end up with 1. But if that makes a little more sense to you, then there's just another strategy. Okay, I'm actually going to give you a third strategy. Or this one's a little tougher, but for the couple of you that might, your brains just think this way, this is great. If you have tangent of x, mathematically, a secant on the bottom is the same as a cosine on the top. Let that make sense to your head. A secant on the bottom, because it's the flip of cosine. I can literally just take secant and move it to the top and call it cosine. I can literally take cosecant that's on the top and move it to the bottom and call it sine. Okay, most people get that. But tangent is a little harder. Tangent is sine over cosine. You can literally make it sine over cosine. And if you're wondering, how does that work? It needs to be sine over cosine just in the numerator. I'm not going to go through the long explanation now, but I assure you it does work. But like I said, let's just let it go at that. This is another possibility that some of you might be getting. Okay, so this was simplifying. Simplifying is when it's your job to just kind of piece it together and make it the best answer you can make it. We actually will do very little simplifying in the future. Instead, we're mostly going to be doing verifying, which I like better because the difference is they tell you what it simplifies to. That's the only difference. They're saying, not only am I going to give you the problem, I'm going to tell you what it simplifies to. That way, you know when you're done. I mean, these were kind of obvious. You got to 1. That's pretty simple. But sometimes they don't simplify to something very nice. So this simplifies to cosine of x over 1 minus sine of x. Somebody might argue that that's not simpler, but it does have sines and cosines, which are generally easier to work with. Again, this simplifies to cotangent. It's kind of nice to know that in advance. But what makes verifying a little harder is you have to be really careful that you don't cross this equal sign. You're still just simplifying the one side. This is just the goal. So I want you to work down. So first of all, I see a secant squared minus 1. Now, if you look back, we have that on our list. Secant squared. It's not on your page, so if you didn't write down all 3 versions of this, then this is still a little hard for you. But secant squared minus 1 is tangent squared. So I'm going to rewrite that as tangent squared. And then a secant on the bottom is the same as a cosine on the top. So I'm going to take this secant and I'm going to move it to the top and I'm going to call it cosine. And because it's squared, I get to bring the square with it. And then I'm going to change tangent to sine squared over cosine squared. And then I'm going to cancel my cosines and I end up with sine squared. When I get the same thing as this side, I write this side, and then I put a smiley face because I'm done. I see kids put checks or anything else. But the goal are the steps. You already have the answer. I'm completely grading you on the steps. If I have to, even for a second, as a math teacher of over 30 years, if I have to look at a problem and say, how did they get that? Then you haven't shown enough steps. So make sure that each step is a clear progression of how you got to the answer. So on this one, I'm thinking to myself, I really want to change these to sines and cosines. That's generally a really great thing to have. So I'm going to change this to 1 over cosine and this to sine over cosine. And I think to myself, oh, this does look great. So now they have a common denominator, and I have 1 plus sine over cosine. And then you might get a little sad because you're thinking to yourself, oh, but it's like upside down and not quite right. So I'm going to show you a trick. This one is definitely a trick, but it comes up all the time. So it's an important trick to learn. And that is if you want to change a cosine to a sine, the only way to do it is if it's squared. So I'm actually going to multiply the top and the bottom by cosine. Now, on the denominator, I have cosine squared. And what can I replace cosine squared with? Cosine squared can be replaced with 1 minus sine of x, sine squared x. And you might be thinking, that still didn't help me. Well, it does, because cosine of x times 1 plus sine of x on top, and then the bottom can be factored to 1 plus sine of x times 1 minus sine of x. So not only are squares great because they can let you go from a cosine to a sine, this is not equal to cosine. Be really careful. That rule only works if it's squared. If it's just to the first power, can't use it. It's a Pythagorean identity. It only works when things are squared. But once it's squared, then you can change its form. And once you change its form, it's factorable. And once it's factorable, you can cancel. And look what I got. Cosine of x over 1 minus sine of x. Now, I am going to do this a second way, but I don't really have a lot of room. So I'm going to erase this page and start over. So if you would like to screenshot it, here's your chance. A second way to do it would be to multiply by the conjugate. So a conjugate, you may remember when you had 3 plus the square root of 2, the conjugate is 3 minus the square root of 2. It's when you have a binomial where the first one keeps its sign, plus or minus, but the second one changes. So I'm going to multiply them both on the top and the bottom by 1 plus sign. Again, this is a trick, a different way of doing it. That gives me cosine of x times 1 plus sine of x. On the bottom, I get 1 minus, the inners and the outers cancel. That's the whole point of a conjugate. 1 minus sine squared x. Hopefully, you look at your identity sheet and you see, oh, 1 minus sine squared x. That's cosine squared x. You are going to want to have those all memorized. And then one of these cosines cancels with one of these cosines. And you get 1 plus sine of x over cosine of x. Now, if you did it this way, you could become really frustrated. You're like, oh, I didn't do anything. I just flipped it upside down. It didn't give me tangents or secants. Okay, so here's a very important point. While you are not allowed to add to both sides, divide by both sides, square both sides, you can work on both sides independently. So I'm going to just abandon that for a minute, and I'm going to start to work over here. I'm not doing anything to both sides. I'm not adding tangent to both sides or something. I'm just changing the format of this one. My point is going to be that it doesn't matter at what point you get these two to look the same. If at any point side A looks like side B, you're done. So it's not that you have to take side B and always make it look like side A or always get side A to look like side B. This is another option. All right, letter C. So I see a cotangent. I always change things to sines and cosines. So I'm going to change this to cosine of negative theta over sine of negative theta. Remember that cosine of negative theta, you can look back on your sheet, is the same as cosine of theta. It is in quadrant 4, so it does not matter. And then sine of negative theta is the same as negative sine of theta. Remember, I'm not pulling that theta out. It's because it's in quadrant 4. And then the negative can be on the top or the bottom. I'm just going to put it out in front. And cosine over sine is cotangent. I write it the same on the other side. And I'm happy that I got a short one. That one's not too bad. D. So I'm going to do a lot of things right away. First, I see a cosecant squared. I'm going to change that to a 1 over sine squared. Ooh, and I was just about to change this to cosine squared, but then I thought, oh, if I distribute, maybe that'll be good. So you're going to have choices and you might see a certain path. You should feel free to follow any path you want. They all lead to the good end, just some of them are longer. Yeah, I'm going to go ahead and stick with this, which is changing this to cosine squared x. And I'm actually going to change the other side too. Remember, as long as you don't do things to both sides, like I can't clear fractions. This, not allowed. Okay, you can't do anything to both sides, but I can work independently on both sides if I want to. So on this side, I'm thinking to myself, I'm going to change this one to sines and cosines. She said that was a good strategy, and it is. So I've changed everything to sines and cosines. I got rid of my reciprocal identity, and I used the Pythagorean identity. And by those three things, I literally finished. So just to offer you a little encouragement, if you're finding this at all challenging or saying, oh, I don't really get these. I really struggled with these in high school. They take us just a certain ability to think, have your mind, memorize these identities, but then be able to put them forward and be able to see a path. So I can't tell you that every problem is the same, and that can be really challenging. So I am trying to give you strategies. Another strategy, change everything to sines and cosines. I'm going to use that one again. This one would be 1 over sine, and then this one would be sine over cosine. Am I selling you on this strategy? This is a good strategy. And then the cosines cancel and the sines cancel, and I get 1 and 1. That was a great one. That was nice. So on this next one, there's a whole bunch of options, but I have to tell you, when I see the square and the 1, I'm always thinking of Pythagorean. So sure enough, 1 plus tangent squared is secant squared, but I want you to be really careful with this next one. We actually rewrote the identity that this goes with 3 different ways. So it was given to you this way on your sheet, and then we subtracted sine from both sides, and we got 1 minus sine squared x is equal to cosine squared x. Or, going back to the original one, you can subtract cosine squared from both sides, and you would get sine squared x is equal to 1 minus cosine squared x. So people all the time are not careful here. They just try and force the hand of one of these identities. But none of these are cosine squared minus 1. I see 1 minus cosine squared, which is close, but it's not what I want. So here's another thing you can do. You can take this and you can put it in just right here. So cosine squared x is 1 minus sine squared x. You could keep coming up with more forms of the identity, but I think you're better off just knowing these 3. And then this gives you secant squared x times negative sine squared x. So that's what that becomes, just as an aside. Negative sine squared x is going to be cosine squared x minus 1. It kind of flips them both around. And then I would change secant to 1 over cosine squared x times negative sine squared x. And that gives me, remember, numerator times numerator, denominator times denominator. And honestly, if I had more room, I would just do one more step and write negative tangent squared x. But instead, I ran out of room, so I'll work on the other side. As long as you're not doing things to both sides, you're good. And remember that tangent squared is sine squared over cosine squared. There you go. But I really want you to be careful of this. I will be looking for places where you throw in a negative because you can't figure it out. It always has to work. So this challenge problem is because we've introduced the natural log. So watch what's going to happen on this one. I'm going to change secant to 1 over cosine of theta. And then you may remember that the natural log of a over b is the same as the natural log of a minus the natural log of b. So I'm going to use that rule. Going back to an earlier chapter, natural log of, notice that I kept the absolute value symbol for the cosine because cosine could be positive or negative, but for the natural log of 1, the number 1 is positive already, so I don't need to do anything for it. And fun fact, in addition to remembering this rule, natural log of 1 is 0. Important thing that you need to remember. So this is 0 minus the natural log of the absolute value of cosine of theta. And of course, that is the answer. You don't really need that 0 there. I was just making sure you knew where it came from. All right, there's another one of these. So now, because these are subtraction, you can put them together as division, helping you study for your final here. And that becomes natural log of tangent of theta, which is what the other side is. So it said challenge. I actually don't think that these, honestly, I think letter F was a lot more challenging. But these two rules are the reason it's a challenge. You may not remember them well. And although we didn't need it on this one, don't forget that the third one is natural log of AB is natural log of A plus natural log of B, in case that comes up on your homework. All right, last problem. A function f is odd when f of negative x is equal to negative f of x. A function is even when f of negative x is equal to f of x. Meaning, I always find that definition so complicated. So in an odd function, if you have a point like 3, 4, then if I do the opposite of x, negative 3, I'm going to get the opposite of y, negative 4. And graphically, it kind of spins 180 degrees about the origin, meaning the origin would have to be the center point. So something like a propeller is odd because it would spin, and when it's in one direction or the other, you don't know which one's which, unless you draw them badly like me and one's oversized. Where an even function is something that opens or closes like a book. Notice it does not have to go through the origin. It just has to have the property that if you have 3, 4, if I do the opposite of x, negative 3, remember last time putting a negative 3 in gave me a negative 4. That's odd. If I put in a negative 3, I still get 4, same y value. That's what makes it even. So when it talks about the 6 trig functions, I personally like to think of them graphically. Sine goes like this. And then it keeps going, but it's hard to keep drawing. So sine is definitely odd. Cosine, I don't know why I did that line there. Cosine starts at 1, goes back up to 1, and then on the other side, do you see it? It's like a book. It's even. But instead of doing it that way, you're more than welcome, if you don't want to think about it graphically, you could just try a point. So tangent of pi fourths is 1, and tangent of negative pi fourths, by the reference angle, pi fourths is still going to be 1, but negative pi fourths is in quadrant 4, and in quadrant 4, tangent is negative. So by that definition, if these are both positive and now they both become negative, that makes it odd. Or if you were already on the graphing track, you might have said, no, it's definitely an odd function. So any way that you think about these, graphically or otherwise. So of course, can we continue with, I was going to draw a new graph, but I think in order to do cosecant, since I always draw sine first anyway, here is cosecant. And of course, you'll see that it's still odd. without drawing its own cosecant graph. For secant, look at that. Can you see how that's even? It's going to be the same on both sides and around the axis. So secant is also even. And it makes sense that they would match their reciprocal functions. And then cosecant, or cotangent rather. So again, you don't have to do it graphically. You can say cotangent of pi fourths is 1. Cotangent of negative pi fourths is in quadrant 4. So I still refer to the pi fourths and get 1, but based on my forecast, tangent and therefore cotangent is negative. So it is odd. All right, that is it for section 9.7. Have a great day.